Today we are just going to discuss about the design of your FR filters using your window techniques. Before starting with the numericals, I will just let you know the design procedure for designing of your FIR filters. We already seen what we mean by an FIR filters, the difference between your IR filters and the FIR filters. So FIR filters is nothing but your finite impulse response type of your filters. In those time finite impulse response of the filters for the designing of your FIR filters, of course we are going with 5 different window methods, starting with your rectangular window, Bartlett window, Hanning window, Hamming window, and the Blackman window. Okay, so with 5 different types of window techniques. So before starting with your procedure, that is starting with your numericals, I will just let you know the design procedure. So what are the steps we have to follow for designing your FIR window filters? Yes, so we can see here the screen which I have shared here. The frequency response of an ideal filter is being mathematically expressed here with the equation that is HD of omega is given by e to the power minus j omega, where omega varying between that is less than omega c. Okay, and it will be 0 for the remaining values. The remaining values, that is omega varying between omega c to pi. Okay, so this is one of the simple mathematical expression which we have to remember for designing of a FIR filter. Coming into the with respect to the theta of omega, that is, we can see the second figure here, the representation, that is what we can call it as a graphical representation of your theta of omega. Here theta of omega, we can see that what theta of omega, that is for omega less than your plus of omega c, the value of your what we can call it as a theta of omega, that is magnitude, is minus omega into alpha. And for the remaining values, that is for omega varying between, that is pi to, or that is omega varying between omega c to pi, the theta of omega is equal to 0. Okay, so here we have to remember the very first one, that is HD of omega, that is e to the power minus j omega for varying between omega less than of omega c. Okay, so what we have to do here is, the next thing is we have to find out the inverse discrete time Fourier transforms, not the just DFT here, it is discrete time Fourier transform, that is the DTFT here, we can see here. For to proceed with the inverse IDFT of your HD of omega, so that is HD of omega, I am trying to obtain my HD of n. HD of n can be obtained by finding out the inverse discrete time Fourier transform, that is what we call it as IDTFT. Okay, so which can be represented by a simple formula that is given by 1 by 2 pi, and that is time varying with respect to integral of minus pi to plus pi HD of omega into e to the power of j omega n into d of omega. We know the DTFT formula. So in that particular DTFT formula, we are trying to obtain the IDTFT of your HD of omega, which is HD of omega, the HD of omega, that is h of omega with respect to the windowing function, okay, into e to the power of j omega n into d of omega n. And we know what is HD of omega from the mathematical expression. HD of omega is equal to what? It is e to the power of minus j omega. So just substituting here in the formula, it will become 1 by 2 pi integral of minus omega c to plus omega c into e to the power of minus j omega into alpha into e to the power of j omega n into d of omega. Okay, so after simplifying this, I'll be getting the what we can call it as HD of n, which can be represented in a simple formula, that is sine of omega c into n minus alpha divided by pi into n minus alpha. This is what we are trying to obtain, that is from the HD of omega. So finally what we get is HD of n is equal to sine of omega c into n minus alpha divided by pi into n minus alpha. That is for the case when n is not equal to alpha. But what about when n is equal to alpha? That is, if I call this the equation number 1, that is equation number 1, the substituting HD of omega as e to the power minus j omega. So this is in the equation number 1. In place of n, if I just letting n is equal to alpha, what will happen? If I let n is equal to alpha, my above equation, that is my integral of this equation, will become HD of omega is equal to 1 by 2 pi into integral of minus omega c to omega c into d of omega. That is nothing but when n is equal to alpha, my hd of alpha will becomes omega c by pi. Okay, that is will be getting two different equations when n is not equal to alpha and when is equal to alpha. When n is not equal to alpha, it will be sine of omega c into n minus alpha divided by pi into n minus alpha. When n is equal to alpha, it will become omega c by pi. Okay, so yes, the next step is in the design procedure. What is the impulse response? I am trying to find out the simple impulse response of any of your filter. That is, here it is an FI filter. So the impulse response of your FI filter is given by what h of n is equal to, that is, I'm trying to find out the impulse response for a finite impulse, that is a finite samples, h of n, which is equal to h of d into n into w of n. Okay, what is w of n? W of n is the causal window that is starting for n is equal to 0 and ends at n is equal to, that is, n minus 1. It can be capital N or capital M, nothing but the same, which I told you in the earlier classes also. So the impulse response of the causal FI filter is given by h of n is equal to h of d of n into w of n, where w of n is the causal window and that it's starting from n is equal to 0 and ends at n is equal to n minus 1. Okay, yes. Then whether it is symmetric or unsymmetric, depending on the type of a function, we have to check whether it is a symmetric about n is equal to alpha or not. Okay, since ht of n is even symmetric, if it is an even symmetric about n is equal to alpha, and the window function, that is w of n, is even symmetric about its midpoint. A midpoint is being calculated. Wow, a midpoint is being calculated by using simple formula, that is n is equal to n minus capital N minus 1 by 2. Okay, a linear phase results, a linear phase, that is a linear phase of h of n will be obtained, and which is even, and that particular even is, once again, it will be symmetric about its midpoint. Okay, it will be symmetric and it will be a linear in nature. Okay, and for obtaining that, we require what? Alpha is equal to n minus 1 by 2. Okay, so we have to remember one more formula for finding out the, what we can call it as the midpoint. Finding out the midpoint can be found with a simple formula, that is n is equal to, small n is equal to capital N minus 1 by 2. Okay, then yes, then we have to remember some of the simple steps for finding out any of the, what we can call it as your h of n. What is that? We have to find out the cutoff frequency. The cutoff frequency, that is nothing but omega c, and that is depends upon the type of the window. Okay, to find out the cutoff frequency omega c, it depends upon the what type of window, as we are using the 5 different types of a window. Depending upon what type of window we are using, we can find out your omega c. Then the next step is the transition window. That is, the transition window of your FR filter is approximately equal to what? It will be equal to the width of the main lobe. Okay, we are seeing the different types of your, what we can call it as the frequency spectrum in the earlier class, and with respect to the main lobe and with respect to the side lobe. Okay, so the transition width of the FR filter is approximately equal to the width of the main lobe of the frequency response of the window what we are trying to use. Okay, so the two things we have to remember here, the first one is omega c depends upon the type of the window function window we are using, and of course the transition width of the FR filter is equal to the width of the main lobe. Okay, it's equal to the width of the main lobe. Okay, and we have to remember this particular table here, that is the following table, that is, it is giving the details about the transition width of each and every type of the window, then the stop band attenuation. Okay, that is a minimum stop band attenuation for different types of your windows. Okay, so we have 5 different types of windows, starting from the rectangular to the Blackman. We can see for the rectangular type of your window, the transition width is 4 pi by n, which is in radians, and the minimum stop band attenuation is 21 dB. Okay, so whenever they are given you the details of your what we can call it as in the numerical, if they give you the stop band attenuation, depending upon the stop band attenuation, I have to select which window I have to get it. For example, in the given problem, if the stop band attenuation is something like 30, if the stop band attenuation is 30, I have to go for the value which is near to that particular value, that is near to your 30. It's near to your 30 is nothing but your 25 is there. That is, I can start from Bartlett window to the Blackman window. Okay, if my value, if it is more than that, that is, if my value is 20, then I can use any one of it. That is, I can use a rectangular window, I can use a Bartlett, I can use a Hamming, any window. Okay, it depends. If it is 80, then I cannot use any other window other than the Blackman window. So depending upon the stop band attenuation, I have to select which window is necessary for me. Okay, so there are some what we can call it as the designed procedures or the steps, what we can call it as the iterative procedure steps. Before starting with the numerical, we have to know this particular steps, what we can call it as the iterative steps. Okay, so I'll start with the simple numerical here. With the numerical, of course, I will discuss the iterative procedure or what we can call it as the steps also. So both the things I will just try to explain here. So instead of explaining the design procedure, I will start with the numerical. In turn, in the same way, means with each and every step, I will explain you the iterative procedure also. Okay, so yes, coming into the numerical here, I'm just taking a simple numerical here, that is design a low pass digital filter to be used. Okay, that is with analog to digital conversion of, that is H of Z structure, that will have a minus 3 dB cutoff at 30 pi by radian second. That is the data whatever they are given is having a minus 3 dB cutoff, that is Kp is been given, that is Kp is equal to minus 3 dB cutoff at 30 pi radians. What is this 30 pi radians? That is nothing but your what? Omega p is 30 pi radians. Okay, so they are given omega p which is 30 pi radians, then they are given kp which is minus 3 dB, and attenuation of 50 dB, that is ks is equal to 50 dB at 45 pi radians per second, that is omega of s is equal to 45 pi radians per second, and the filter is required to have a linear phase, and the system uses a sampling rate of 100 samples per second. We can see they are not specified what type of filter, whether it is an IR filter or an FR filter, but we can make out whether it is an IR filter or an FR filter by looking into the word, that is the filter is required to have a linear phase. So the word linear phase, from the word linear phase, we can tell that the filter what I am trying to design is a finite impulse response type of your filter. Okay, so if we see that the filter what I'm trying to design is an FI filter, I will try to take down the details here. So it is a digital filter, so I have to convert my digital data into an analog data. So first I'll write down my omega p, that is 30 pi radians second, omega s is 45 pi radians per second, t which is given, that is 1 by 100 samples, that is you can see samples, sampling rate is 100 samples per second, so t is equal to 1 by 100. Kp is minus 3 dB and Ks is equal to minus 50 dB. What is the first thing we have to do? First thing is convert the whatever the banded digital frequencies using the formula. That is, what is the formula we have? Omega is equal to W of omega, that is W is equal to omega into T. Okay, so we have to use the simple formula to convert into the banded digital frequencies. Okay, to convert into a banded digital frequencies, so omega is equal to omega into t, that is W is equal to omega into t. Yes, we know the data, substituting omega here, that is 30 into 1 by 100, it will become 30 by 100, that is nothing but W of p is equal to 0.3 pi radians and W of s is equal to 0.5 pi radians, that is of course 45 divided by 100, it will be 0.4 pi radians per second. Okay, that is the first step. What is the next step? I have to select the type of the window to the highest, that is the highest in such a way that the stop band attenuation should exceed your Ks. What is Ks here? Ks is 50 dB. So I have to select the window in such a way that my K should exceed your value 50. So looking into the table, if we see that, if we look into the table, from the table we can see the type of window, the transition width, and the stop band attenuation. So which is the value greater than 50 here? My Ks is minus 50 dB here. Okay, so which is the value greater than 50? That is your value, which is Hamming window. So for Hamming window, it is 53, and for Blackman window it is 74. So I can use any of these two windows. That is nothing but I can use an Hamming window, or else I can use a Blackman window for designing what? For designing the filter with the above frequency specifications. So I can use both the things, but I'll be looking once again into what we call it as a transition width also. What is the transition width here? The transition width is, for an Hamming window, it is 8 pi by n, and for the Blackman window, it is 12 pi by n. So I'll be selecting the proper, what we can call it as the window, the proper window here. That is, I'll be going for is Hamming window. Why I'll be going for an Hamming window? Because the transition width is lesser here. My transition width for Blackman window is 12 pi by n, but my transition window, that is the transition width for your Hamming window, is 8 pi n. So I will go for your Hamming window for this particular filter. Okay, so we can see here, to meet a stop band attenuation of 50 dB, we have two choices, that is in the form of Hamming window or as in Blackman window. Our choice is Hamming window because it has a lower transition width compared with your Blackman window. Okay, so first thing is I'll be looking for Ks. My Ks is 50 dB, so I'll be selecting the what is the window more than your Ks. More than Ks is Hamming and Blackman. In this, I'll be selecting what? Hamming because of the transition width. Okay, yes. The next thing, what is the next step? The next step is to find out the number of samples in the window. To find out the number of samples in the window, that is the second design procedure. We can see here, the first step is select the type of window. Yes, we have done it. The second step is the number of samples in the window is been found using the simple equation, that is omega s minus omega p, which is greater than or equal to k into 2 pi by n. Okay, and my k value is also varying on the integer, and it is equal to 2 for rectangular window. K will be equal to 4 for Bartlett Hamming windows, and for K is equal to 6 for your Blackman window. So totally we have totally 5 windows. We can see rectangular window, Bartlett, Hamming, and a Blackman. For rectangular, it is K is equal to 2. For Bartlett, Hamming and Hamming, it is K is equal to 4. And for Blackman window, the K is equal to 6. Okay, so of course I have to find out the number of samples. For finding out the number of samples, I am using this particular formula, that is omega s minus omega p, which is greater than or equal to k into 2 pi by n. Here I have the window which I am using here is an Hamming window. So for Hamming window, my k value is equal to what? My k value is equal to 4. So substituting k value is equal to 4, and omega s as what? 0.045 pi, omega is 0.3 pi. I'll be getting the value of n. Okay, so if you see in the numerical, yes, I'm substituting as omega s minus omega p, that is 0.45 pi minus 0.3 pi, which is greater than or equal to k value is equal to 4 into 2 pi by n. My value of n is greater than or equal to 53.5. That is, after substituting here in this equation, I'll be getting my n value, the capital N value. The capital N value is 53.5. That is, it is an what? Odd number. Okay, and when it is an odd number, of course, when I'm trying to go for a next higher case, that is the next higher value, I'll be going for the next odd value itself. Okay, not the even value. So my n value will not be 54. My n value will be 55. That is the next odd integer. Okay, so the next higher odd integer, which will be 55. Okay, so instead of that is 53.5, what is from the calculation, my next odd integer value will be 55. So my n value is equal to 55. What is the next step? In the third step is in the design procedure. If you look into the design procedure, the third step is to find out the impulse response of an FR filter. To find out the impulse response of an FR filter, we will just show you the procedure here. You can see the impulse response of the FR filter can be found with this, that is h of n is equal to h of d of n into w of n. Okay, h of d of n into w of n, and we know what is h of n here. H of n is given by sine of omega c into n minus alpha divided by pi into n minus alpha into omega of n for n is not equal to alpha, and for n is equal to alpha it is omega c by pi. Okay, that is omega c by pi, which we have seen in the derivation earlier. Okay, so I have to find out the impulse response of your FR filter. So coming to the what, yes, we can see here, coming to the numerical here, that is to find out the frequency response of the desired low pass filter, that is h of d of omega, which has been substituted in the form of e to the power of minus j into w of alpha. Okay, and here my omega is for less than omega c, and it will be 0 for omega varying between pi to omega c. Okay, which we have seen in the earlier frequency response curve. Okay, frequency response of any desired low pass filter is given by this particular formula. In this, I have to find out what is my value of alpha. What is alpha? How can we find out alpha? Alpha is equal to capital N minus 1 by 2. What is capital N here? That is the order what we have got here, which is 55. So it is 55 minus 1, it will become 54. 54 by 2, it is 27. Okay, so my value of alpha, it is 27. So it will become e to the power of minus j 27 into omega. Okay, so I just substituted the alpha value here in the equation. Okay, what is the next thing? We know the formula hd of n is given by what? It is given by the two things. One is your what we can call it as hd of n can be obtained with the two parameters. One is hd of omega, and it is multiplied by e to the power of j omega. And what is hd of omega? Hd of omega here, it is e to the power of minus j omega into alpha. So I substituted here in this particular formula, it is hd of n is given by 1 by 2 pi integral of minus omega c to omega c e to the power of minus j omega into alpha e to the power of j omega n into d of omega n. After substituting any of, we know the formula what we got in the earlier expression. So it need not to explain all these things in the numerical. When we start with the numerical, directly I can come down to here, that is I can come down to the expression that is nothing but sine of omega c into n minus alpha divided by pi into n minus alpha, which we have derived here. Okay, the same expression I am just taking here. So we can see here, this is the expression, that is hd of n expression, which I am considering in my numerical. Okay, so I am just considering that particular case in the numerical. So it will become sine of omega c into n minus alpha divided by pi into n minus alpha for n which is not equal to alpha, and for n is equal to alpha, we know that what it will become, it will become omega c by capital N. Okay, yes, but the impulse response of an Hamming window is given by what? I have to consider the both the thing, the impulse response of an Hamming window, that is h of n, that is impulse response of any of a causal FR filter, is been given by, we know the formula, h of n is equal to hd of n into my window function. Okay, so h of n is given by what? hd of n into w of n. W of n is the window function. Which is the window I'm considering here? I'm considering an Hamming window. So I have to represent what is the Hamming window equation also. So if you see here, h of n is equal to hd of n into w of n. That is an Hamming window function. Okay, so in the next impulse response formula, I'm substituting h of n is equal to hd of n is this, what we got here, that is sine of omega c into n minus alpha divided by that is n minus alpha. Okay, then which has to be multiplied with what? Which has to be multiplied with your Hamming window function. If you look into the Hamming window mathematical expression, the Hamming window mathematical expression is being given by the expression that is 0.54 minus 0.46 into cos of 2 pi n divided by n minus 1 for n varying between 0 to n minus 1, which we have seen in the earlier classes. Okay, so I'm just considering that particular Hamming window function, and it is omega. Next case is that is omega c by pi for n is equal to alpha. Okay, for n is equal to alpha, it is omega c by 5. Now what is the next thing we have to do? It is a trial and error procedure. We have to choose your omega c for passband with passband frequency values. Okay, so I have to select with the trial and error procedure. We have to start with, we have to choose your omega c, that is omega c, which will be equal to your omega of p. Okay, we can see in the design procedure. I will show you the design procedure here. Okay, we can see here, once we find the impulse response of the FI filter, then for the trial procedure, that is we choose alpha is equal to n minus 1 by 2 and omega c is equal to omega p. Okay, since n is odd, the frequency response of the FI filter is being computed using this particular formula, which we have seen in the very first numerical what we have done in your FI filters, which is given by h of omega is equal to the power of j omega into n minus 1 by 2 into h of n minus 1. In the earlier numerical, I have given as n or m. Okay, need not worry, both are same. That is capital M, I can give as capital M or capital N. So it is h of n minus 1 by 2 plus summation of n is equal to 0 to n minus 3 by 2 into 2 into h of n cos of omega into w of n omega into n minus 1 by 2 minus of small n. So this is the formula what we are trying to use for the frequency response of an FIR filter. Okay, yes, the same formula I'll be considering here, and I'll be trying to do with what we can call as a trial and error procedure. With using trial and error procedure, these two equations, I'm trying to plot the frequency response curve, and the frequency response curve normally it will be appearing something like this. Okay, which we can see in this particular figure. Okay, so the normally the frequency response curve will be something like this, and that too that is as expected at omega is equal to omega p, the passband attenuation will be always exceeds minus kp, that is minus kp, which is being given. Okay, dB. Hence we slightly what we'll do, will increase your omega c. Then as using in equation number 1 and 2, we again will try to plot the magnitude response, and we will try to check for the passband requirement. Okay, if it doesn't satisfy, once again we will repeat this, what we can call it as a iterative procedure. Okay, the same procedure we have to follow here. Okay, in the numerical also. So once we find out your n, then we'll be trying to find out your hd of n, that is nothing but your h of n. Once we get your h of n, then the trial and error procedure with omega c is equal to omega p with the passband requirement, and finding out your alpha we can get from n minus 1 by 2, which is equal to 27. So from those two equation and one more equation, that is the frequency response of or your FR filter for n is equal to r, that is this particular formula, will try to plot the trial frequency response curve. We can see here the frequency response curve, and at what omega p at 0.35 pi, my kp is equal to minus 3 dB, we can see. So it is, you can see here, it is found that at omega is equal to 0.3 pi, the attenuation is more than 3 dB. Okay, hence what we have to do, slightly increase your omega c, and using equation number 1 and 2, plot the magnitude response once again. Okay, so in the examination, what we have to do here is, we have to start finding from the what type of window I am trying to select. That is, first we have to convert into a banded digital frequencies, then try to select the window based on the attenuation and as well as on the transition width. Then find out the value of capital N. Finding out the capital N value has been this particular formula, and based on the value of your Hamming window with respect to the K value, find out your capital N. Then find out the value of your what we can call it as the alpha value. Then find out this particular equation. Okay, find out this particular equation, that is nothing but the impulse response equation, impulse response for the particular window. Here we are trying to find for an Hamming window, so it is h of n into sine of omega c into n minus alpha divided by n minus alpha into my Hamming window function. I have to remember the Hamming window function. The Hamming window function is given by this 0.54 minus 0.46 into cos 2 pi small n divided by capital N minus 1. Okay, so then we know the normal procedure, iterative procedure, so we can just show how the frequency response curve will be for any of your given window. Starting with the second numerical here, that is the frequency response of a desired low pass filter is given by h of d of omega, which is equal to e to the power of minus j into 3 of omega, sorry, where omega is for less than pi by 4, and for omega varying between pi by 4 to pi, it is 0. Okay, what we have to find? We have to find the frequency response of the FIR filter. Okay, we have to find the frequency response of the FIR filter, and here they are given using your rectangular type of your window. There's examination they are given, it is a rectangular type of window, so I have to remember with I have to start with the rectangular type of window function itself. Okay, what is the first thing? I'm trying to find out your alpha here. How to find out your alpha? Once again, alpha has been found with the formula that is n minus 1 by 2. Okay, so n minus 1 by 2. But we know that alpha has been given here, not n. Alpha has been given from the alpha. What is alpha here? We can see e to the power of minus j 3 into omega. Here 3 is nothing but your alpha. Okay, so alpha has been known here, so I can find out the capital N. So substituting alpha is equal to 3 here, so it is n minus 1 by 2, which is equal to 3. We'll be getting capital N value as 7. Yes. What is the next thing? We know the function hd of n is given by this, that is 1 by 2 pi into integral of minus pi by 2 into, that is minus pi by 4 into to the power of pi by 4 e to the power of minus j 3, that is e to the power of minus j into 3 omega into e to the power of j omega n. So we know all those things. I'm directly substituting in the formula, that is sine of omega c into n minus alpha divided by pi into n minus alpha. In that particular formula, I can directly substitute here. Okay, so what will happen? It will become sine of omega c is equal to what? Omega c is equal to pi by 4. So it is pi by 4 into n minus alpha. Alpha is equal to 3. So it will become pi by 4 into n minus alpha divided by pi into n minus alpha. We know that hd of n is given by sine of omega c into n minus alpha divided by pi into n minus alpha for n which is not equal to alpha, and for n is equal to alpha, it will become just omega c by pi itself. Okay, so omega c by pi itself. So here for n which is not equal to alpha, that is n is not equal to 3, by substituting the value of alpha here, it will become what? Sine of pi by 4 into n minus 3 divided by pi into n minus 3. Okay, or else it will be just 1 by 4 for n is equal to 3. The next thing is I have to find out the impulse response. To find out the impulse response, what I have to do? Impulse response of the Causal FR filter is been given by what? H of n is equal to hd of n into my window function w of n. So h of n can be obtained using what? hd of n into my window function. My window function is a rectangular window, that is w of r of n. And my n value is also varying between what? N, capital N is equal to 0. So my samples is varying between 0 to 6. So my h of n is equal to hd of n into w r of n. And when my R of n, that is nothing but what the samples is varying between what, for samples varying between 0 to 6, it will be 1. We know that for a rectangular type of window, the magnitude of a samples will be always 1. Okay, so for a rectangular type of window, my for n is equal to 0 to 6, it is 1. So what I have to do here, if you just have to substitute in the above equation my w of r of n, and I have to multiply with your h d of n. So I'll try to plot in a form of a simple table here. In this particular table, what are the parameters? That is, parameters are small n, that is the samples starting from 0 to 6, and h of n, that is my h of n is nothing but my impulse response. How to find out the impulse response? H of n is equal to hd of n into w of r of n in this case. Okay, so what is r of n, w of r of n? W of r of n will be always the same, the magnitude will not change here. So for a rectangular window, so it is 1 completely. So I have to substitute, I have to calculate what is my h of n. Okay, yes. How to calculate my h of n here? Yes, yes. In the first case, substituting my h of n is equal to what? Replacing here, that is hd of n. In this hd of n, I have to substitute the values starting from 0 to 6. Okay, substituting the values from 0 to 6, I have to calculate my what is h of n value. What is the first thing I'll be doing? Substituting what n is equal to 0. For n is equal to 0, it will become sine pi by 4 of minus 3 divided by pi of 0 minus 3, that is nothing but pi of minus 3, and which has to be multiplied with your window function w of r of n, which is equal to 1. Okay, if you substitute in your calculator, keeping in the degree, that not in degree, it is in radians. So substituting the values from n is equal to 0 to 6, I'll be getting my h of n value. So my h of n value will be 0.075. Okay, my h of n value will be 0.075 for n is equal to 0. Similarly, substituting for n is equal to 1, 2, 3 up to the value of 6, I'll be getting my h of n values. Okay, I'll be getting for n values. I can just you can call this as hd of n itself. A d is missing here, need not to worry. Okay, because in both the cases it is same, because I'm multiplying hd of n into my window function w of r of n. So I'll be getting the same function, that is h of n itself. Okay, so my hd of n will be the same as of your h of n. Okay, yes. So substituting from 0 to 6, I'll be getting h of n. Of course, w of r of n is 1. So my final h of n will be same as your hd of n. The next thing, I have to find out what we call it as the frequency response of your FI filter. The frequency response of your FI filter is being given by the same formula. That is, h of omega is given by e to the power minus j omega into n minus 1 divided by 2. Okay, this is 2 here, don't get confused. We have already returned, we have already solved one of the numerical in the earlier classes also. Okay, I'm just considering the same expression here. So it is e to the power of minus j omega n minus 1 by 2 into h of n minus 1 by alpha plus summation of n is equal to 0 to n minus 3 by 2 into 2 into h of n cos of omega into n minus 1 by 2 minus of n. So substituting here in this particular formula, we know that my alpha, that is this complete term, which will become e to the power of minus j 3 into omega, that is n minus 1 by that is n minus 1 by 2, which will become what, n minus 1 by 2 we have substituted, so it was nothing but 3. Okay, so e to the power of minus j 3 omega into, okay, that is h of 3 plus summation of starting from and substituting the value of n here. What is n? N is equal to 7. 7 minus 3, that is 7 minus 3 is 4. So 4 by 2, 4 by 2 is 4 once again. So I'm substituting the value of n is equal to 0 to 2 here. Okay, that is h of 3 plus summation of n is equal to 0 to 2, 2 into h of n into cos of omega into 3 minus n. Okay, I've just substituted all the values, capital N value I have substituted here, so it will become w of 3 minus n. Okay, and this expression, once again substituting from n is equal to 0 to 2, I can replace, that is with what is h of n, everything we have calculated here, we know what is h of n. So substituting all those things, I'll be getting my final expression, the final frequency response of an FR filter. Final frequency response of an FR filter will be e to the power of minus j3 omega into h of 3. We know what is h of 3 here. You can see here that is 0.025. Yes, substituting 0.025 here plus sampling, that is substituting the n value from 0 to 2. So what I have to do, 2 into h of 0. We know h of 0 is equal to 0.075 here. Okay, that is multiplied by 2. So substituting all those values here, the value what I will be getting is 0.45 cos 3 omega plus 0.3182 cos 2 omega plus 0.45 into cos of omega. So this is the frequency response of the filter for your given specification using your rectangular type of your window. So